Now, before we move on, we can briefly summarize, brief summary. That stands for what we've done. If we've got a matrix A that reduces to this, then we can easily write a basis for the row space, just this row and this row. And of course, 0, 0, 0 is not a member of any basis. So there's our row space. And we can find our null space just by multiplying, solving the equation. This matrix times an x vector equal to 0 vector. That gives us these two equations and three unknowns. We have a free variable. We're going to call x3 the free variable since it appears in both of the equations. So we're going to say x3 equals t, and then we solve for x2 and x1. x2 is going to be negative 1/2 t, x1 is negative 1/3 t. We could use any t and get the components of a basis vector. So it's simply we use t equals 1, and that gives us the basis vector negative 1/3, negative 1/2, 1. There's x1, there's x2, there's x3. And I'm not sure why I rewrote it, but that's okay. We verify that this is orthogonal to this, and this is orthogonal to this. Make this a row and this a column, or vice versa, and multiply them, you're going to get 0. Make this a row and this one a column, doesn't matter which one is which, and multiply it, and you're going to get 0. So these are orthogonal. It follows that any vector in the row space, being a sum of multiples of this and this, will have 0 dot product with this vector, so that the entire row space is orthogonal to the entire null space. We then sketch a picture. The null space is just multiples of this vector, okay? So I did a multiple of the vector. 6 times the vector is negative 2, negative 3, 6. So if x is in this direction, say x1, x2, x3, just like x, y, z, and you can think of it that way if you like. You go negative 2 units in the x direction. So if the origin is here, you go 2 units this way. Okay? And then 3 units in the negative y direction or negative x2 direction, well, that's going to be 3 units this way. So we go 2 units this way, 3 units this way, and then we go 6 units up this way. And that vector is going to be tilted back something like this. And that's what I've tried to depict here without going into a lot of detail and trying to make a really finely constructed picture, okay? And I'd probably have trouble making a really good one. Then we depict the two vectors in our row space. 3, 0, 1, well, that's 3 units in the x1 direction, no units in the x2, 1 unit in the x3 direction, so that gives us a vector from here to here. And the 0, 2, 1, no units in the x1 direction, 2 units in the x2, 1 unit in the x3, that's the purple vector. So those vectors would look something like this and this, and here's our plane. And that's the plane spanned by these two vectors. I didn't attempt to shade the plane. I made a better choice of the vectors here if I wanted to make a good picture, because the orientation of the coordinate system isn't particularly conducive here. Okay, well, if VR is a vector in the plane, some linear combination of this vector and this vector, and that's what I depict by this red vector. And Vn is a vector in the null space, which means just a vector in the direction of this line. If I multiply the matrix A by VR plus Vn, well, that's by linearity of matrix multiplication. I'm going to get AVR plus AVN, and Vn is in the null space, and the null space was determined by the condition that the vector, the matrix multiplied by the vector is 0, okay? So this is in the null space, so that's going to be 0, so you end up with just A times VR. Okay, now we go on to another example. And I'm not going to include that in this summary, okay? I'll include that in the next summary because it's kind of a new problem and I haven't completed that problem yet.